Significant about, we've been talking about let me start over. We've been talking about probabilities for quite some time, right? That's what this whole stats unit has been about so far. What's unique about the probabilities that we're going to talk about today is these probabilities only have two outcomes. So a simple way to think about it is if you're flipping a coin, you're only going to get heads or tails, right? So there's only two outcomes, thus binomial, okay? Now, if we talk about rolling a dice, there's 6 outcomes when you roll a die. If, let's just say, so that's not binomial, but if I change it to this, if you roll a 6, that's you win, or whatever. So now what happens is it's turned into a binomial. If you roll a 6, you win, it's a success. If you roll anything else, it's a failure and you lose. Does that make sense? So now I turned it into 2 outcomes, a success and a failure. And so you can turn almost everything into 2 different outcomes if you wanted it to. If I'm drawing a card from a deck of 52 cards, and I draw a king, or that's what I want to do, I want to draw a king. If I draw a king, it's a success. If I draw any other card, it's a failure. Thus, it's binomial. Now, some other things have to be true in order for it to be a binomial as well. For example, the second item on the list is it says the trials are performed n times. What that means is you need to have a fixed number of trials. What examples of that would be, you're going to roll a die 5 times. You're going to flip a coin 10 times. You're going to draw 5 cards from the deck. It tells you a specific number of times that you're going to actually do something. So that's also what makes it binomial. Trials need to be independent. And what that means is when you flip a coin, let's say you flip a coin once, the probability you're going to get tails is 50%, right? If you flip it again, what's the probability you're going to get tails? 50%. And if you flip it again, it's 50%. The probability doesn't change based upon the number of times you do this, and therefore it's independent. It works. The probabilities remain the same all throughout. An example where the probabilities would not remain the same is if you, like say you had a deck of cards. You draw a card out and without replacement, meaning like you set it aside and then you go to draw another one. Well, now you only have 51 cards in your deck, therefore the probability just changed. Does that make sense? Did I say 51?
Yeah.
Okay, I thought I said 54 for a second, but okay, 51 cards in the deck. Perfect. And then the last thing is the probability of success and the probability of failure need to add up to be 1. So what that means is if you flip a coin and you're trying to get tails, that's going to happen 0.5. You know, that's the probability. The probability of a failure would be if you get heads then. That's going to happen 0.5. And you add those together, it ends up being 1. Kind of common sense. So we're going to look at some of these and just say, okay, are they a binomial or not? So the first one says a quarter is tossed 4 times. We know that the fixed number of trials, which is nice, okay? You're interested in the probability that shows heads exactly 3 times. So the success is getting the heads. The failure would be getting tails. There's only 2 things going on. And the probabilities are going to add up to be 1. So this one, yes, it is binomial. The next one says, given that 40% of the people who come to a certain store on Saturday make a purchase. By the way, if 40% make a purchase, how many are not making a purchase? 60%. Good. So it doesn't state that, but it's implied. The manager is interested in the probability that the first 50 people make more than 20, that more than 20 make a purchase. So it gives us a fixed number of trials. Okay. This one would also end up being binomial. Now I like this next one because it says a penny is tossed until it shows tails. You're interested in the number of tosses required. Do you know how many times you're going to toss this coin? No, so this one would represent something that's not binomial because we don't have a fixed number of outcomes, or sorry, a fixed number of trials.
So number 2, why is it binomial? It's like the first 50 people like their question and made it purchase versus no purchase.
Yeah, it's either they purchase it or they don't. They purchase as a success. They just need 20 out of that 50, yeah, to actually make a purchase, at least that, yeah. So this one's not binomial because it doesn't have fixed number of trials. Okay. A single die is rolled 10 times. We know the number of trials. You're interested in the probability of that 3 of the rolls result in a 6. So rolling a 6 is successful. Rolling anything else is not. The trials are independent. This one ends up being binomial. We'll just go over one more. Okay, so I think you guys will kind of get it. Cards are drawn from a deck without replacement. This is the key word. You're interested in probably that of the first 9 cards, 2 are spades. If you don't replace it, it can't be binomial because your probabilities are not independent. Okay? So I'm going to abbreviate. Probabilities are not independent. Does that kind of make sense to you guys? Probabilities are not independent. So I'm going to keep moving on just because of the sake of time. When we go to the next slide, there's several formulas on here. And for your next test, you're actually going to be provided with a formula sheet. So it's actually going to be on a separate sheet of paper. Because when we get into the stuff now, we keep adding more and more formulas, and it's easier just having a separate sheet of paper when you're testing. This first part is what we're going to talk about tomorrow. I left the more difficult part for tomorrow. This bottom part is what we're going to talk about today. Now, we've talked about expected value already, and expected value is just the number of, on average, what would happen in different situations, okay? And we've always taken the probability of something happening times the number of outcomes. So when we get to something like this, expected value, this n is the same n that's referring to up here and the same n down here, right? So they're all representing the same thing. But n is going to be the number of trials. So if you get to a problem and you're like, oh, it doesn't state the number of trials because you're trying to find the expected value, it's not binomial, so you can't do it. Does that make sense? The p in every case, whenever you see it, is the probability of success. And lastly, so what I just want to restate is this n is the same as that n. This p is the same as that p. And then the q is new too. So p is the probability of success. Q is going to be the probability of failure. So it looks like that. Notice we're using the same variables in the formula that we're going to need tomorrow. All right, so I think well, we just talked about expected value, but way back when, didn't we already do standard deviation first semester? And it's a lot of work. I don't know if you remember that. This is all we're doing for standard deviation here, the square root of these variables. So it's not going to be as intense as the last standard deviation you just did. So this is what a problem would look like on your homework. Okay, there's going to be 4 parts. We're only answering the first 2 parts today. So it says if 20% of the population is left-handed, a group of 16 people are being observed. We want to know what's the expected value. By asking this, it's saying, I got to change this question. Let's just ignore this one. But what is the expected value? We're trying to find out how many people out of that group do we expect to be left-handed. So when I'm set it up, I'm going to say, okay, and that's always n times p. That's what we just discussed on that last slide with the formulas. So I'm going to take the number of trials, 16 people we're looking at, times the probability of it being successful, which in this case is left-handed. So I multiply by 0.2 or 0.20. Okay. Now, obviously, when we do this, we're going to get a decimal. And you can't have a fraction of a person, but please just leave the decimal for right now so I can see your work. So it's saying out of a group of 16 people, approximately 3.2 people should be left-handed. You follow me? Now, the next part you're going to have to do is the standard deviation. And they use this symbol that's called sigma for standard deviation. You might remember that from first semester too. And what we have to do here is we're going to take the square root of n times p times q. So then we're going to say, okay, the number of trials is still 16. The probability of success is still 0.2, which means the probability of failure, meaning right-handed, sorry right-handed folks, is going to be 80% or 0.8. So now what I need to do is I just need to put this in my calculator. And some of you will have a calculator like mine, where we'll just put everything underneath the square root and you're just fine. But let's say your calculator doesn't continue the square root over. Be very careful. In that case, you would need parentheses around this whole thing. Okay, so if you have a calculator different than mine, you might need parentheses around that whole thing. So you get 1.6. Now, we're going to do more with these numbers tomorrow, okay? But I just want you to be able to get them today. That's it. So that's the only part we're going to do today. Then I want to go on to the next problem. We'll do 3 examples. How about that? So this one changes. It says you roll a fair die 5 times. Okay, the number of trials is 5. She wants to roll 6. What's the expected value? So expected value, out of 5 rolls, that means how many times should she expect to get a 6? Our number of trials times our probability of success. Number of trials was 5. The probability of it being successful, I'm going to leave as 1/6. A 6 is only going to occur 1 out of 6 times. So when I multiply that, I get 0.833. Just looks like that. Now the standard deviation, so sigma of x, is where we're going to take the square root of all of these. And it's okay if you have fractions instead of decimals. Our last example had decimals. So this time we're going to say, okay, times 1/6. 1/6 is successful. Do you guys know how to figure out what's not successful? If 1 out of the 6 outcomes is successful, that means 5 out of the 6 is not successful or considered to be a failure. You can still put it into your calculator just like that in fraction form. And you don't have to have parentheses, but you can if you want. If your calculator doesn't carry the square root over the top of everything, you need parentheses all around all of that. And we end up getting the same answer. That's just kind of a fluke in the problem that I made up. That won't usually happen. And again, we will do more with these 2 values tomorrow. Okay. We'll do one more example. A bag of M&Ms contains 20 red ones, 24 green ones, and 23 blue ones. A child takes 5 M&Ms and selects them one at a time. The child wants to get red M&Ms. Now what we're assuming is he actually returns it to the bag. But there's probabilities are independent in this case. So the expected value in this case, number of trials is going to be 5. And the probability of it being successful, well, there's 20 red ones out of a total of how many? Looks like 67. So that's what I'm going to have to multiply. Okay, so I get 1.49. That's the expected value. If I'm drawing 5 M&Ms out of that bag, I should expect that about 1.5, 1.5 of them is going to be a red one. The standard deviation, and I don't know if you remember, standard deviation, how it varies depending on how spread out your data is. Do you kind of remember that from first semester? So I'm going to do 5. The probability of it being successful was this. So what that means is the probability of it not being successful, if 20 out of the 67 outcomes were successful, the leftover 47 outcomes are not successful. And then we just have to substitute or put it into our calculator. There we go. So I get 1.02.